All right, in this section we look at vector fields. In the past we have looked at functions of a particular form, particularly something like t of r comma theta is equal to xy. So here we have a transformation, which is a function of two variables into a vector valued function, x comma y. And specifically by this we mean that x is equal to r cosine theta, y is equal to r sine theta, our polar coordinates transformation. So what we're seeing here is that this transformation takes two variables r and theta, and this transformation takes a value of r theta like 1 comma pi over 2, for example, and turns it into the point x comma y, or transforms it into the point xy. X is equal to 1 cosine of pi over 2, y is equal to 1 sine of pi over 2, which is equal to the point 0 comma 1. All right, so this is what we've looked at in the past. We've looked at a vector valued function in two variables. Okay, now we're going to look at vector valued functions in two variables, but we're going to reinterpret them. Okay, a vector field, we're going to now consider functions denoted f with an arrow over them of x comma y. Okay, and there will be two entries to these. This could be a two-dimensional vector field, or our vector valued function could be a function of x, y, z, function of three variables into three entries, so into three-dimensional space, and there would be an f1, an f2, and an f3, and each of those entries is a function of x, y, and z for I going from 1 to 3. Okay, so these are the kinds of functions that we're going to look at now, vector valued functions, vector valued functions in a certain number of variables. Okay, and we're going to interpret these functions. We're going to call these vector fields, and we will give a geometric description of them on the next page. So we have two types of vector valued functions, and it's just up to their interpretation for how they will be treated. Okay, so in this section 16.2, we're going to focus on vector valued functions in two variables called vector fields. And what you're seeing over here on the left is an example of a vector field. You're noticing that just a bunch of arrows, and there is an arrow at every location in space, at every point in the plane x comma y. So if I were to change and make this a different function, you can take each of these two entries of the vector field, which is just a vector valued function, and you can make them any functions of x and y that you want. And then you will get different arrows, and the arrows change according to the two entries of this function. So if you wanted x times sine of y, you could see what would happen, or you could make, like cosine of x times y. Right? Any functions that you want there, and you start to get interesting shapes and that happen. Okay, so let's dig in a little bit to vector fields and look at some special cases. Let's look at some special cases. Okay, so here we are. What we're looking at here is the vector field that we just saw a second ago. The vector field f of xy is equal to x comma 0. So if we think about this as some points, at the point x comma y, we have the vector x comma 0. That's how we're interpreting this. So if you look at, for example, the point 1, 2, here is the point P is equal to 1, 2, and the vector at that point P is given by f of 1 comma 2, which is x is 1, y is equal to 2, but the vector field says that you're supposed to have a 0 in this entry. And so when we're thinking of this as a vector, we're thinking of this 1, 0 as the vector at the point. And so right here, there's a vector that points in that direction, the 1, 0 direction, which is the x direction, okay? And in fact, no matter what point you pick, because of this 0 here, this vector field says that the vector is going to always point in the x direction. But we can see that because of the location of the x here, the direction of the vector changes with the value of x. So for example, if x is equal to -2, right, and y is equal to 0, there would be a vector that is pointing to the left, right, because the vector at the point Q, -2, 0, because x is negative, the vector v at the point Q is -2, 0. Okay, and that is what we are seeing right here with this arrow. So if a vector field is just a bunch of vectors at a variety of points. Okay. Now you can get some interesting vector fields with some pretty simple looking functions. Here we have the vector field f of x comma y is equal to -y comma x. So here if you look at the point, let's say 6 comma 0, okay, then the vector field at 6 comma 0 is y is equal to 0, so we'll put a 0 in the y position, x is equal to 6, and so we have 0, 6, and 0, 6 is a vector that points in the y direction. Okay. We're not really, in these pictures, we're not drawing these vectors to their length. If we were doing that, this vector f at 6 comma 0 would be a vector of length 6. So I would have to draw this vector like this of length 6, but the picture would look really, really crummy at that point. So essentially we're just drawing these kind of vectors kind of scaled a little bit. Okay. So we can also see that there is another vector at this point at 0, 6. The vector at 0, 6 would be -6 comma 0. And that is a vector that is pointing to the left. So here we have, with this pretty simple, straightforward vector valued function, we're seeing that we can get the ability to model some vector fields that have this kind of circulatory nature. Here we can kind of see that this vector field is kind of a very simple function for circular motion. Okay, so let's look at a couple more examples. So these kind of examples are going to be good to keep in your mind. Here we have a vector field that can kind of circulate. Right? There's some circulatory motion in there. And we have other vector fields, okay, that even pretty simple looking vector fields, f of x comma y, two-dimensional vector field x comma y. So this says that whatever the point P you pick is, let's say you pick 2, 2, that the vector at that point P would be the value of the vector field at 2, 2, which would give you 2, 2. And so here we're seeing the point P is equal to 2, 2. There is a vector at that point that is pointing in the y equal x direction. Okay, so this vector field, no matter what, except 0, 0, if you evaluate this vector field at 0, 0, you get the 0 vector. So any other point that you pick will be a vector that's radiating outward from this center. Okay. And so this could look like the electric field of a point charge, for example. So I'd like to call this like an explosion vector field. It's radiating out from the center, out from a center. Okay, and here the vector field doesn't have to have functions in it for its entries. You could have the vector field f of xy. You could have the first entry and the second entry of the vector field. Instead of being a function of xy, you could just have a constant. You can have the second entry of the vector field, instead of it being a function of xy, it could just be a constant. And this vector field indicates that there is like perhaps wind or something that is coming from a very certain fixed and constant direction. So no matter what point you pick, the vector field is pointing in the same direction. Okay, so it is these vector fields that are going to serve as the basis for all the types of integrals that we are going to look at in the next couple videos and the next week. So ends our introductory video on vector fields.